This is the lecture number 8. Let's begin with the summary of the previous lecture. Last lecture is mainly based on the textbook section 2.21 and 2.22. And then the first, I introduced the first postulate. And the first postulate says that in quantum mechanics, the quantum state of the particle is represented by a vector in a Hilbert space. And then I gave you two types of the example of the quantum system or the Hilbert space. And then the first example was the two-level atom. And then two-level atom is the simplified version of the multi-level atom, which is more realistic. But in practical purpose, we are only interested in putting the manipulating the electron between these two energy levels. So in that case, you can just ignore all the other multiple levels with higher energy levels, and then to control the quantum state of the electron in the atom, then we are using the electromagnetic field, which sometimes exists in the form of the photon, or sometimes it is in the form of the just the microwave. And then the what is important is the whether it is a photon or the microwave. What we really need to control is the frequency of those electromagnetic waves. And then the frequency is basically related to the energy difference between these two energy levels. Another example of the quantum system was the polarization of the light. And then the I showed you that the polarization basically behaves like a vector in a Hilbert space. And then in the previous lecture, I only gave you the example of the vector with the real valued components. But in principle, there is no reason why we cannot have any of the complex number as the linear coefficient of those vectors. And then the in generalized form, the coefficient can be also interpreted as the shifted phase of the sinusoidal wave. So I explained to you the meaning of the phase. So, and then we also introduced the second postulate, which was related to the evolution of this vector in time. And then in simple statement, we can say that the quantum state or the vector in the Hilbert space is mainly evolved through the or the quantum initial quantum vector is transformed by the unitary transformation. And then this one is more likely the statement which is frequently used in quantum information. But if you want to know the origin of this kind of behavior, then we have to resort to the Schrödinger equation, which is kind of a continuous time version of the second postulate. And then the Schrödinger equation looks like this one. And if we solve the this equation, then we obtain this kind of solution. And this kind of solution has the exact form like what we said in the postulate 2, meaning that the initial state is connected to the later state in time through the unitary operator. And then as long as this H, which is a Hamiltonian, is in the is the Hermitian operator, then the this exponential of the complex type of the Hermitian operator is actually the unitary operator. So today we are going to continue, and then we will introduce the third postulate. I know that the first two postulates were already embarrassing, but probably based on some of the analogy to the classical mechanics case, yeah, you could make some kind of intuitive understanding. However, the third postulate is the most embarrassing part, and then yeah, and then you know that Einstein never accepted this kind of third postulate, and then until he dies, he did not accept. And then I will talk about it a little bit more later. And then Niels Bohr, who is also a very famous physicist for the discovery of the quantum theory, he also said that anyone who is not shocked by the quantum theory has not understood it. Also, the famous physicist Richard Feynman also said at some seminar that he said that I think I can safely say that nobody really understands quantum mechanics. Yeah, so yeah, it is not only you. If you are embarrassed by the this third postulate, and then if you actually don't have any problem, then you probably didn't understand what I'm talking about. Okay, so yeah, based on assuming such kind of situation, let's try to interpret what the third postulate say. So in the first two postulate, we know that the particle will be will be described by some vector state. Then the third postulate is about the measurement of the given quantum state. And then for the measurement, yeah, we will generally measure some value like speed or the position of the mass or the energy of the mass. Yeah, so those are generally represented as a variable. And then in quantum mechanics, we always assume that for each of the measurement, there will be also corresponding Hermitian operator. And then yeah, here I only say omega, but it is actually Hermitian operator omega. And then what happens if we really measure something? Yeah, for example, what happens if we measure the position of the some mass? Then that means that there will be corresponding Hermitian operator corresponding to the measurement of position, and then that Hermitian operator will have the eigenvectors and the eigenvalue, and then the measurement value can be only one of the eigenvalues, not any other values. And then we already are familiar with the concept that when we measure the energy of the electron in the in a hydrogen atom, then the energy values are not continuous, but they are discrete. And then how is that? How can we predict those values? And then those values are actually the eigenvalues of the energy operator. So yeah, I will get back to that point a little bit further in the next page. But yeah, this statement says such kind of situation, and then the next question is how often. Well, there are many different. There might be many different eigenvalues. Then, which value shall we measure at each of the measurement? And then the next statement says that the probability of measuring this omega sub I is proportional to this value, this kind of expression. And also, the most embarrassing part in the end is that the quantum state after the measurement, the quantum state of the system will actually change. Yeah, so after the measurement, the quantum state probably won't be in the same state before the measurement, and then the final state is always the eigenvector corresponding to this eigenvalue. So yeah, and then this situation is called as a collapse. So I know that the overall statements are still embarrassing, and then this statement already has many components. The first thing is that there should be Hermitian operator corresponding to the measurement, and then measurement result is the second fact is that the measurement result should be the eigenvalue, and then third fact is that the probability of that measuring that value is described by this one, and the fourth fact is that the state after the measurement is the one of the eigenvectors. So let's consider those things in more details. If we are given some Hermitian operator corresponding to the measurement we want to do, and then in principle, we should be able to find out the eigenvectors and eigenvalues which will behave, which has this kind of relation to the original operator. Then one thing we can, and once we are given these eigenvectors, then generally we can use those sets of the eigenvectors as the orthonormal basis of the space. So yeah, in that case, any arbitrary quantum state of some particle will be extended into the summation of all the eigenbases with some coefficient, something like this one. And let's think about some concrete example. So let's assume that there is two some measurement operator has the two eigenvectors, and then let's call it as omega 1 and omega 2. In that case, some arbitrary quantum state will be also represented as the linear combination of omega 1 and omega 2 with some coefficient. Then what the third postulate says is that if we measure the value corresponding to the measurement Hermitian operator omega, then we will either obtain omega 1 value or omega 2 value. And moreover, let's assume that so when we so for this quantum state, it actually is represented as a superposition of these two possibilities. So yeah, when it is in this state, then it is natural to think that if we measure some quantity, then yeah, we cannot tell whether we will obtain omega 1 or omega 2. So everything seems to be a little bit confusing or random. Then there should be still some kind of rule, and one of the rule is that how often do we get the omega 2 or omega 1 value, and that one is basically determined by this coefficient, which probably is reasonable. Yeah, so if you have some quantum state, and then if the quantum the state vector representing the quantum state of the some object has the much larger coefficient in front of this state rather than this one, then it is natural to imagine that you will if you make a measurement, you would have more chances to have to measure this value rather than this value. So yeah, it is reasonable to guess that the probability to measure omega 1 will be probably related to C1, and then probability measuring the omega 2 will be also related to C2. And the next question is how they are related. Well, yeah, C1 and C2 can be even a complex number. So yeah, one option we can think about is the magnitude of this one. And then what the third postulate says is that the probability to measure the omega-1 is not proportional to the magnitude of this coefficient, but it is proportional to the magnitude of this one squared. So this is what the third postulate says. And then how can, once you are given this psi vector, how can you find out C1? Well, C1 can be found by easily by taking the inner product between psi and omega-1. Then we will obtain C sub 1, and then then from this one we can calculate the square of those value. And then what the third property says is that the probability to measure omega-1 value is proportional to this value, while the probability to measure omega-2 value as a measurement result is also proportional to the omega-2 psi and squared. And finally, the most embarrassing fact is that even though when before our first trial of the measurement, the quantum state might be like this one, and then assume that, and then I mentioned that the all we can predict is the probability to measure either omega-1 or omega-2. But nature never says, or the quantum mechanics never says next time what value you will measure. So the actual selection of the value is kind of random. And then let's assume that when in our first measurement, in our first trial, we measured omega-2. Then what is more reasonable? If you, right after your measurement, you try to measure the same object one more time, or same quantity one more time, then is that more natural to obtain omega-1 next time or omega-2 next time? Probably omega-2 again. And then so once you prepare this kind of quantum state or the superposed state, and then your first trial for the measurement might be random between these two possibilities. But once you obtain one of them, then if you keep repeating with the same object again and again, then you should be able to measure the same value continuously. So to satisfy such kind of situation, it is much more reasonable to assume that right after the first measurement, the quantum state won't remain in the form of the superposed state. But if once we measure the omega-2, then right after that, the quantum state will actually become omega-2 only. So once we have this kind of state, then there is no chance that we will be able to measure omega-1. So so before the first measurement, it might be in the superposition state, but once the measurement is done, then it will collapse into this one. And so people call it as a collapse process. When the right after the measurement process. And I know that all of this explanation is still vague. So let me give you some example using the polarization measurement. One of the intuitive example for the quantum state is the polarization. So let's try to let's imagine that we are thinking about the polarization here. So you might even think that this 0 is represented by horizontally polarized light, and then 1 is represented by the vertically polarized light. And then if we have quantum state whose quantum state is either zero, or in other words, it is horizontally polarized, then what do you expect when you measure the polarization? Yeah, of course, it should be horizontal or zero. So, and then from here, yeah, it is obvious that there is no chance that you will measure number one case. So this kind of situation satisfy this argument such that yeah, here it is only say the proportional, but because there is zero coefficient in front of one, so the probability of measuring is zero is one, because if you calculate this calculation, then this part will become one, and the square of one is one. So the proportional probability is proportional to one for zero case, but for the one case, because the coefficient is zero, the probability is proportional to zero, which means that the it will always we will always measure zero only. And then after the measurement, what will be the next state? Still zero, because we measure the horizontally polarized light, and then it will continue to remain as a horizontally polarized light. So that's perfect for this this kind of description. Then what about this case? Again, yeah, now we have perfectly we have a vector which is perfectly aligned to the one basis, and then in this case, if we measure, then we will only get a one, and if we keep repeating the measurement, we will continue to get one only. The next, the more tricky situation is like this one. So I intentionally made assume the vector which is relatively close to zero compared to one, and then in this case, what? And then yeah, especially I can because this is vector. So yeah, this kind of vector can be represented as a linear combination, something like similar to this one, and then what do you expect if you make a measurement? Because it is close to zero, but not perfectly zero, do you expect that you will measure 0.1? Well, yeah, that is the case when if it is a classical measurement, but it is a quantum state. And then in this case, what quantum mechanics says, the third postulate says, is that we can either measure 0 or 1, not 0.1 or 0.05 or yeah, whatever floating number. It should be uh, um, either 0 or 1. And then yeah, at, if you hear such kind of argument, then you might be a little bit embarrassed. But if you look at the example, which I will show you in the next page, then that might make more sense, because what we can only measure is either horizontal or vertical. So we cannot measure between V or H or V. And then, yeah, in this case, then what does this amplitude or the coefficient? Yeah, so in the quantum mechanics, the coefficient of the linear combination is generally called as an amplitude rather than the coefficient. Yeah, so yeah, I will frequently call this part as a probability amplitude. So yeah, don't get confused if I use such kind of terminology. And then, what's the meaning of the probability amplitude? Well, yeah, according to the postulate 3, the probability of measuring 0 is proportional to 0.9, while the probability to measure 1 is proportional to 0.1. So yeah, that means that if we prepare this kind of superposition state, and then if we try to measure the value, then and then if we repeat such kind of preparation and measurement about 100 times, how often do you expect that you will measure 0? Well, on average, probably 90 times you will measure 0, and only for 10 times you will measure 1. Yeah, and then then the quantum mechanics tell you when you will actually measure zero or when you will measure one when the given state is in superposition state. No, yeah, if it is definite state like a zero or one, then yeah, you know that you will always get zero or always one. But if your state is superposed state, then yeah, the quantum mechanics does not tell you what value you will get next time. Yeah, so that's the tricky part of the quantum mechanics. However, yeah, even if you started with this superposed state, if you once you measure and then you yeah you repeat such kind of preparation and the measurement many times, but at some time, yeah, you again prepare the same type of the superposition state and measure make the measurement, and then you just happen to measure zero. Then without preparing the superposition state again, if you just repeat the measurement of the um, polarization, then you will continue to get a zero value. Yeah. And then in that case, the only way it will continue to give you a zero is that the quantum state, which was originally superposed, like this one, it will collapse to this zero definite state right after measuring zero. Yeah, so that is what this third postulate says. And yeah, for the another example, what about this state? If we prepared the quantum state, which is sitting right between 0 and 1 vectors, then what do we expect if we prepare this kind of a superposition state and measure? We actually don't know. Sometimes we will get zero, sometimes we will get one, and then the probability to get either zero or one is 50% for each. Yeah, so and for these cases, we call them as a superposition state. And then yeah, let's also consider about the more concrete example for the polarization. So with the polarization, yeah, we are mostly familiar with the concept of the polarization of the light. So assume that we start with some randomly polarized light, or maybe yeah, it might be the 50% of the horizontal polarized component and the 50% of the vertically polarized light, or yeah, in that case, because it is proportion, it will be either diagonal or anti-diagonal state. And then here, what this cube does is it separates two types of polarization. So if you started with the horizontally polarized light, then it will pass through the polarizing cube. However, if your input polarization is vertically polarized, then it will be reflected by this one. So this polarizing cube does the kind of measurement work. And then if we start with some 45 polarization or diagonal polarization, then half of the power will be yeah, then because we know that the diagonal polarization is the equal superposition of horizontal polarization and the vertical polarization. So the half yeah, the horizontal component corresponding to half of the polarization will will be transmitted, while the another half of the polarization, which is vertically polarized, will be reflected by this polarizing cube. And yet, but we know that inside this light, yet all the energies are being carried by the photons. So what really happens is there are a lot of particles like in the form of the photon. And then what this describes is that half of the photon will be transmitted, while half of the photon um, uh, 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 will be reflected, and half of them will be transmitted. So if we didn't have the picture of the photon, then the measurement result might be a little bit, yeah. So yeah, without considering the particle picture, then you might say that if I call this horizontally polarized case as the zero value, zero measurement, and then vertically polarized case as the measurement of one, then because we have half of the power is transmitted to zero and half of the power is transmitted to one. So on average, you might say that, well, yeah, once we measure the polarization of this one, we kind of measure the value of 0.5 or something like that. However, if we cannot claim such a situation because again, yeah, the light is composed of the particles, and then for this case, um, yeah, one of the important property of the photon is that photon generally do not split to two particles. So each of the particle can either be reflected or to be transmitted, and then it cannot just go between them. So yeah, for this case, we might have this kind of situation, but then we can imagine attenuating the power of this laser or the light. Then if it is it is only half of them, then the number of the photon being reflected will be also half, and then transmitted will be also half. And if we reduce the number of the incoming photon even further down to 2, then only on average only one of them will be reflected and then one of them will be transmitted. The most challenging question is, what happens if I just start with the single photon? Well, yeah, then if it is a classical case, then you might say that yeah, this photon might be split into two paths. But no, photon cannot be split into two paths because whenever we shine the laser or light, the either transmitted light or reflected light still has the same frequency with the incoming light. And then what that means is that um, we know that the amount of energy being carried by the single photon is calculated by the um, HNU or well, let's use the app for clarity. Yeah, so H times the frequency. However, if the the energy of this single particle is being split into two paths, then the uh, the energy being carried by one of the reflected particle should be F over 2, and another should be HF over 2. Then that does not make sense because that means that the frequency of the reflected light should have the frequency of F over 2 rather than F, which means that it is complete different frequency. And the same for this guy. So the only option to satisfy the concept of the energy conservation law is that the this particle either goes to being transmitted or being reflected, but not half and half. So yeah, considering such kind of situation, so if we started with this diagonal state, diagonal polarization, then the only option is that this one can either be transmitted or reflected. And then in this case, yeah, again I said that I will define this one as a zero state and define this one as a one state. So when it is being transmitted, then we will obtain the zero measurement value of zero. And then if this photon is being reflected, then our measured value is one. So that's the yes. So if you think about this kind of measurement, then the third postulate makes much more sense, because that even if the quantum state is in a superposed state, the measurement result only gives us one of the basis, uh, the eigenvalue corresponding to one of these basis vector or eigenvector, and then right after the measurement, yeah. So this polarizing cube will serve as the measurement device, and then assume that if it started with this superposition state, and then it is being transmitted. Then we know that once it is transmitted, then the transmitted light should have the only the horizontally polarized light, polarized horizontal polarization, because if it has any other component of the polarization, then it cannot be transmitted. It should actually be reflected. So yeah, even though the incoming light might have both components, once it passes through the this polarizing cube, or if it is reflected by this polarizing cube, then there is no other choice for the polarization. But this should have the H, and this should have the V. So once it has the H, then if we put another polarizing cube after here, then what will happen? Then in that case, it should always be transmitted. And then if I put another measurement polarizing cube, then it will be also transmitted again. So that will continue to transmit it. And then that means that even though we started with the superposition state, once the first measurement is done, the resulting state will be collapsed into one of them, yeah, one of the H or V. When I also learned about the third postulate, the first one of the question I had was why the probability should be proportional to the magnitude scale of these coefficients rather than the only the coefficient or the magnitude only. So yeah, let's think about some example related to this. As an example, let's think about this kind of vector. Yeah, so yeah, the this vector can be decomposed into this probability amplitude, and for this case, it is natural that if we calculate the scale of the absolute value, then it is 3/4, and then similarly the scale of the absolute value, it will be 1/4. So the summation of these two cases will lead to the 1, which means that the probability of measuring either 0 or 1 becomes probability of 1, meaning the 100%. And this interpretation still makes sense if we consider measuring the value of this vector in different bases. Yeah. So for example, we might consider using this tilted base, and then let's call this vector as 0 prime and 1 prime. And in this case, the same psi vector, yeah, now it is um, along this new vector, and then here I'm assuming that the length of this one is 1. Well, yeah, you know that yeah, the overall numbers means that the length of this one is 1. And even though I just drew this with different lengths, but I'm assuming that this new base is also normalized. So actually they should be the same length. And then that means that this original state can be also represented in the new basis with this in, so um, probability amplitude of 1. And then for this case, if I change the measurement basis into this tilted one, then we know that the coefficient or probability amplitude is still 1. So if we calculate the square of the magnitude, then it will become 1. So yeah, independent of whether we use this basis for measurement or this basis, new basis for the measurement, we always obtain that the total probability of measuring something is always 1. However, if we use the amplitude, just the absolute value of the amplitude rather than the square of that absolute value, then there is some problem, because in that case, this only the square root of 3/2 is about 0.86, and then yeah, this is 0.5. So if we add these these value together, then they are definitely larger than 1. And then so depending on which basis I measure, then if I use a 0 and 1 basis, then the probability looks larger than 1. While if we use this new basis, then it will still be the 1, because whether we have a square or not, 1 is still the same as 1. So in this case, we have some problem that depending on the basis, the total probability is not constant. So if you think about this kind of situation, then um, 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 the square of the absolute square of the absolute value or the square of the magnitude makes more sense for the probability. And one more thing I forgot to mention is that for this example, I intentionally normalize the coefficient. So the summation of the square of each of the probability amplitude is 1. And then yeah, of course, the third postulate only says that the probability of measuring this one is only proportional to the probability amplitude squared, but it doesn't say that it is equal. But if we normalize the coefficient, then the probability is simply the same as the square of the probability amplitude. So it is it is conventional to normalize all the vector. Um, yeah, yeah. So in quantum mechanics, we generally prefer to normalize the vector rather than just using some other length of the vector. Let's also think about some other example of the measurement. Probably, you are also familiar with the concept, concept of the two-level atom by now. And then, yeah, we generally, I generally use this kind of picture, and then use this kind of notation. So in principle, the the quantum state of the electron inside the two-level atom can be represented by this kind of expression. So what happens if I measure the quantum state of an electron? Well, first of all, we should define what do we mean by measuring 0 or 1 state in a two-level atom. Well, generally what we mean is that each of the energy level will be occupied by the electron, and then measuring the 0 or 1 means that measuring the energy level of each of these state. And then how is and then when we measure the each of the state, then what kind of measurement value do we get? Well, probably the most reasonable measurement value is the energy. So then, yeah, the next question is, yeah, what's the best way to represent the energy? And then, yeah, we can get the hint from the concept that when the when the electron decays from the excited state to the ground state, we have some accompanying um, photon being emitted from this decay process, and then this the amount of energy being carried by this photon is represented by the frequency, and then the amount of energy of that one is either we use h uh, h frequency, or sometimes more often it is represented by the Habar omega, which is the angular frequency corresponding to f. And then, yeah, based on this idea, yeah, so yeah, here, yeah, we use this notation only to represent the energy difference between these two energy level, but the absolute value of each of the energy level can be still represented in terms of the um, in terms of the angular frequency. If there is some kind of absolute zero energy state, then with respect to this zero energy state, this might have some energy difference, and then we would label that energy difference as the Habar omega naught, and then there is another omega energy difference with respect to the ground state, and then we would use this notation of Habar omega 1. So these are the values we would generally obtain as the energy value of each of the energy level. And then for the notation, we generally know that eventually HABA will be multiplied to the angular frequency. So we frequently use only the angular frequency as the eigenvalue to label the eigenvectors. But we should not forget that the actual um, measurement value for the energy is the Haba omega. So the next question is, then what is the measurement operator corresponding to the two-level atom? And then now the question is, can we build the energy operator which will whose eigenvector is omega naught or omega 1, and then for each of the case and then when you measure this energy level, then the this well, yeah, so and then each of the eigenvalue, yeah, these vectors should be the eigenvector. So how can you build such kind of operator? It is actually quite simple. Yeah, if you just write down in this way, so yeah, here, yeah, 0 is the same as the omega naught. So this is the eigenvector corresponding to h bar Haba omega naught, and then the same vector the bra bra vector corresponding to this one, and similar for the this one state. Then this is simply the measurement operator corresponding to the energy operator and energy measurement. And then yeah, here I intentionally use the notation of H, which means the Hamiltonian, because that yeah, in the previous lecture I mentioned that the meaning of the Hamiltonian is actually the total energy, and then here the total energy is corresponds to the total energy being carried by the electron. So yeah, this is natural notation to represent the Hamiltonian of the two-level atom. in the previous page, we considered about the measurement device for the polarization. And then at that time, we simply say that either horizontally polarized or vertically polarized light being measured. But to represent the measurement in terms of the operator, yeah, we cannot use this kind of alphabet, but we need some kind of value. So let's assume that if we have some kind of measurement device which will produce the output will be 2 if you measure horizontally polarized photon, and then the output value will be -1 if you measure the vertically polarized light. Then what is the proper operator representing such kind of device? Well, it is quite simple or straightforward. If you remember how we constructed this operator, then the corresponding measurement device will look like this one. So it is just multiplying the measurement value to the projection operator for horizontally polarized vector, and also multiplying on -1 to the projection operator for the vertically polarized vector. Well, in the previous page, I constructed either the energy measurement operator for the two-level atom or the polarization measurement operator for the photon. But typically, um, yeah, in most of case situation, we don't construct the measurement operator by itself, but generally they are given or the measurement operators are generally guessed from the corresponding classical classical mechanics model. For example, we know we have well-defined concept of the energy, and then there is some kind of one-to-one correspond, not exactly one-to-one, yeah, but roughly the correspondence between the classical um, um, measurement value like momentum, and then there is some special operator corresponding to the momentum, and also position has such kind of operator, and then energy is generally the summation of the kinetic energy, which is generally expressed in terms of the momentum, and also the potential energy, which is also represented um, by the position. So each of them, most of them has its own corresponding operator in quantum mechanics, and then and even for the angular momentum is the cross product between the momentum and the position operator. So yeah, typically, if you are interested in some value for your measurement, then generally you can guess from the classical equivalent value. And then yeah, if, even if you just hear what I described, if you did not learn about the quantum mechanics before, then probably you don't understand. You actually cannot cannot understand what I'm talking about. And fortunately, yeah, you actually don't need to understand those details when you are interested only in if you only want to understand the um, quantum computing programming or quantum logic. And yeah, there are also a few questions you might still ask about the third postulate. Yeah, for example, I said that a measurement operator should be Hermitian, and I already mentioned that one of the reasons is that because measure we know that the eigenvalue, the measured value will be eigenvalue of the given operator. So, and then we know that all the eigenvalue of the Hermitian is the real value, and then the typical measured value should be real. So that's kind of a reasonable connection. And another, and also in the previous example for the two-level atom, I mentioned that um, the measurement um, um, measurement operator for energy is also called as a Hamiltonian, and Hamiltonian also appears in the middle of the Schrödinger equation, and um, then I also mentioned that the Hamiltonian should be Hermitian. And then why is that case? And then I already also kind of mentioned that eventually we know that the quantum state, the evolution of the quantum state is generally connected through the unitary operator. And then for this solution to satisfy such kind of relation, then this part should be Hermitian. And then yeah, this part basically comes from the Hamiltonian. So if the Hamiltonian is not Hermitian operator, then we cannot satisfy this kind of requirement for the unitarity. And then so that's why it is important that the Hamiltonian is the should be the Hermitian. And another and then next question you might ask is why should the quantum state should be evolved by the unitary operator? And the answer, the simple answer is to preserve the total probability. And what do I mean by that? So you remember one of the property of the unitary operator is that it preserves the length of the vector, and then you already saw that the total probability of the even if you have a psi of the um, psi vector, which is the linear combination of some state alpha and beta, we know that the total probability of measuring anything can be obtained by the square of the absolute square of the sum of the square of the probability amplitude. And then in that case, we know that if we measure something, then we either should obtain a 0 or 1. So the summation of these value should be 1. And the problem is this quantum state will be evolved by the unitary by some operator. And then if that operator is not unitary, meaning that if the new vector which is evolved by some operator, um, then if the size of the vector length of this one is not conserved, then or preserved, then the total and then yeah, this might appear with some new vector state like this one. And then if the square of r and then the square of the absolute value of delta is, if it is different from 1, then there is some conceptual problem, because the only measurement option we have, or the only measurement result we can have for this kind of quantum state is either 0 or 1. And then if the total probability of measuring either 0 or 1 is different from 1, then we are missing something, because there is no other possibility of measuring some other value, but all the summation of the probability is different from 1. Then there are some cases which is not being explained by this quantum state. So to avoid such kind of problem, the only option we can have is, instead of having just arbitrary operator, we need some unitary operator. Then because the unitary operator preserves the preserves the size of the length of the vector because of this relation. Because of this relation, and this is just the identity operator. So if the original state or original psi, the vector size or the inner product of itself was 1, then uh, the resulting state will also have the same length of the length of 1. So um, I know that all of these explanation is somehow sketchy. So yeah, you might still have a lot of questions about the quantum mechanics. But the point of this class is not teaching the quantum mechanics by itself, but I just wanted to give you some taste of the quantum mechanics. And then, yeah, last thing I can also consider is the following. So what I have described up to now is generally called as Copenhagen interpretation. And what do I mean by that? So in early 1900, people started to observe some new things like Planck's black body radiation problem or the photoelectric effect, and then all of those things could be only explained by the concept of the quantum um, quantization of some kind of energy, and yeah, all the physicists were confused. So they gathered together, and then they wanted to decide, or they wanted to figure out how what will be the reasonable way to interpret or how to calculate things, and then all those postulates, yeah, I just described, like all those three postulates was kind of discussed in this meeting, and then but it was not it wasn't happy because as you feel as you also might feel, um, well, yeah, the we yeah, in third postulate, I said that the probability of measuring some kind of eigenvalue, or yeah, the all the measurement value is the eigenvalue of some kind of operator, and then the the probability of measuring some eigenvalue is proportional to the square of the probability amplitude, and so forth. Yeah, so many of them are counterintuitive, and yeah, people didn't want to accept those kind of interpretation. Yeah, but yeah, many of the experimental results, yeah, pointed to that direction. So yeah, there were a lot of confusion, and then even though you know that Einstein correctly interpreted the phenomena of the um, photoelectric effect, and then also the black body radiation problem, he actually did not like the quantum mechanics, especially when when yeah, especially about the measurement problem. Yeah, it was really confusing because yeah, for most of you also feel the same way that um, if I measure some, yeah, even if original state was superposition state, if I measure something, then um, the quantum state suddenly collapsed to, yeah, one of the eigenbases, and then that does not make sense in the daily life experience. So there were a lot of complaints from the Einstein, and Einstein even came up with a clever idea of how he can disprove many of the Copenhagen interpretation. And then the most famous one is something called as EPR state. And then EPR means that Einstein, Podolsky, and Rosenberg, those three people wrote some paper, and then they created some imaginary quantum state, and then say that how can you how can you measure or how can you make this kind of state? So you cannot make this kind of state. So there is some flow um, in the framework of the quantum mechanics or the Copenhagen interpretation. And then instead of following the Copenhagen interpretation, which says that the measurement of the sum value is kind of random, and then yeah, most of the physicists didn't like the concept of the completely random. So yeah, Einstein even says that he is not convinced that the God does not play any dice. So and then yeah, and yeah, one of the funny reply to this comment is that Bohr said that stop telling God what to do. Yeah, so yeah, and then yeah, there was a lot of debate, and until Einstein dies, he never accepted such kind of Copenhagen interpretation. But what is irony is that the EPR state or EPR pair served important role in the development of the quantum mechanics. And then nowadays, people actually can create the entangles state frequently. And then you have the measurement result always support the Copenhagen interpretation. However, there were also other alternative way to explain what has been observed at the time, and then yeah, well, and then yeah, one of the theory is called as hidden variable theory, and then what hidden variable theory is the following. So even though, yeah, for example, if you are in the laboratory and then you are doing some measurement, and then if you measure different value, even if you believe you did everything correct or the same, then the quantum mechanics is saying that, well, probably what you are measuring is the superposition state. So that's why you are getting some random different result at every time. But one possibility is that the system you are trying to measure might be sensitive to the temperature of the laboratory, and then maybe you were not including those temperature measurement into your in maybe you are not careful about those temperature. So even though there is additional variable which determines the result, and then yeah, that one really and but when you don't know about that variable, then you might believe that it is just random. So hidden variable theory basically assumes that you cannot measure everything, but there is some unknown variable which we are not aware of, and then that is the reason why we get such kind of weird result. However, yeah, up to now, yeah, whenever people come up with well, yeah, yeah, most of the hidden variable theory was somehow rejected by the experiment because people yeah somehow produce some ideal quantum state, and then depending on the measurement result, you can decide whether yeah hidden variable is correct or the Copenhagen interpretation was correct. But for most of case, for all the cases, yeah, still at least up to now, yeah, Copenhagen interpretation, the prediction based on the Copenhagen interpretation gave us the correct answer rather than the hidden variable theory. And then, yeah, we will also see some of the hidden variable theory in the later part of the this semester. And another way to explain the that behavioral collapse, collapse of the quantum state is multiverse theory. So whenever we are making some measurement for the superposed state, what what the multiverse theory or the many world theory says is that um, whenever there is some measurement, the world will split into two or two multiple world. So in one world, you are measuring 0, while in other world, you will measure 1. And each of them are parallel to each other, and then they are so. And then you just happen to live in one of this world rather than the other world. So um, this even though this kind of idea sounds very weird and then maybe unrealistic, but somehow because that means that whenever I do anything, yeah, even though I was not aware of that I was making measurement, but a lot of interaction is also related to the measurement. So um, there will be a lot of split of the world, and then yeah, probably yeah, it's not easy to imagine such kind of a split of the world. So but the one of the reason people believe this might be the best way to describe the measurement um, measurement behavior in the quantum mechanics is because this only by assuming that there are multiple worlds which has different result, then the people somehow this kind of situation somehow gives a fair chance for each of the different situation. So depending on your belief or whatever you want, you can believe any of these interpretation. But the point is, whichever you choose, the result probably won't be changed. So yeah, if you are really interested in which in finding out which theory is more which theory is correct, then yeah, you probably should study some more physics. But in this class, my goal is not to determine which theory is correct, but what I want to teach you is that how yeah, what is how to interpret or how to predict the result of some circuit. So and then for the correct prediction, then yeah, Copenhagen interpretation is good enough. So yeah, I won't go through any details for this. Finally, occasionally, yeah, you will also see this kind of expression whenever when our measurement operator is given like omega. Then what is the meaning of this kind of calculation? Well, yeah, let's say that let's consider that we find the eigenbasis corresponding to the omega, and then we try to expand some arbitrary quantum state using this eigenbasis. Then you will obtain this kind of yeah. Eventually, you will have this kind of expression, which is composed of the eigenvector multiplied by some probably amplitude and the summation of them. And then the arbitrary state will be appear as a summation of all these terms. Then the next thing we can, yeah, and then to figure out what is the meaning of this kind of expression, then all what you can do is just to plug in all of these expansion on onto the to the left and then to the right. And now yeah, what we then yeah, we can continue the calculation further, and in this case we can move this because it is a linear operator, so this operator can be directly multiplied or applied on the this cat vector. So we will have this kind of summation of this part first, and then we also note that this is also being multiplied to the entire summation. So there are these are the double sum case, and then for the inner summation, inner sum, then this this bra vector can be directly multiplied on this omega operator, because the c sub I is just a scalar value, so it can be pulled out of the this multiplication. So the internal summation will look like this one, while the external summation will be the sum of each of these summation multiplied by this factor. And then now what we can think about is, we know that each of omega sub I is the eigenvector of this one. So if this omega operator is applied on this one, then this combination will be replaced by the omega sub I. Yeah, so this will be omega sub I multiplied by omega sub I. And then, yeah, this is a scalar value. And then this bra vector will be multiplied on this one from the left-hand side. Then oops, yeah, then, sorry. Then this one, and then when this one is also multiplied entire part, then this one will become omega sub I, omega sub j, and then omega sub I. And then we know that this is just the Kronecker delta function. So the entire that internal summation will be turned into this kind of expression. And then we know that the summation of the summation, including the Kronecker delta inside, will be just replaced by the full expression with the and with the I subscript, I index will be replaced by the J index. So the final result will look like this one. And then what is the meaning of this product of these two values, like this one? That is the meaning, that is the expression for the, well, this is the square of the absolute value of C sub j, and then square of the absolute value, where the square of the absolute value of the product amplitude is means that the probability of measuring the j's eigenvalue. So the total summation means that you are multiplying the possible measurement value multiplied by the probability of measuring this value. So what do we call this kind of summation? It is generally called as expectation value of this random variable. So because here the measurement result looks appear randomly. So when you are given some random variable, and then if you want to obtain the expectation value of that random variable, then this is a typical expression. So the entire expression like this one means that the expectation value of the measurement corresponding to this measurement operator. And then similar expression for the classical situation is also following. So if we have some function f of x, and then we know that the variable x has the probability of p of x, then the expectation value of this function can be generally obtained by multiplying this function and then the probability of having X, and then the so this expression is very similar to here, but that's not the only the similarity, because when we are representing the expectation value of a function, then we generally put this function between the bracket. So if you compare this expression with this expression, they also look similar to each other. So yeah, that is why that is one of the reasons why people also prefer to use the bracket notation, because this shape looks very similar to this classical expectation value expression. Well, maybe yeah, that's not the that should not be the only reason why we are using the bracket notation, but maybe this might be one of the motivation why we are using this kind of notation. Okay, so I will stop today's lecture here, and then continue in the next lecture.